Inverse functions are like the inverse operations. They're the functions that undo other functions. So like the inverse operation of addition is subtraction, of multiplication is division, that sort of stuff. Functions can have inverses as well. Two relations are inverses if and only if one relation contains the element b comma a whenever the other relation contains a comma b. What do you notice about these two coordinates? They're just flipped. So if your a's or if your x's become y's and your y's become x's, they're inverses. So the graph of an inverse will also be a reflection over the line y equal to x. So when which we are about to do, we're about to graph the inverses. We should end up with a nice reflection across this diagonal line y equals to x. Every single one of those coordinate points, which I've already plotted for you, should flip right over that. Here's how that happens. For f of x, it gives us all the coordinates. And for the inverse, which you would call f inverse of x, with a little -1 up there, you just literally flip-flop the x's and y's. This would be -1, -2. This would be 3, 0. This would be -3, 1. This would be 2, 4. Do you see how I've just literally flip-flopped the table?
So you don't change the sign?
Don't change the sign. You just truly invert the table. So if we plot those points, -1, -2, it is now a reflection across this diagonal line of that other dot. Do you see that? I mean, besides the fact that my drawing is like not great. If we do the next one, 3, 0, that's a perfect reflection of its opposite, 0, 3. If we reflect -3, 1, that is a perfect reflection of its opposite pair, of its inverse pair. And then same thing for 2, 4. If we plot that one, it is a direct reflection across this diagonal line of 4, 2. So that's all we're doing today, is looking at functions and their inverses. It's going to be flip-flopping x's and y's back and forth to show that the graphs have inverses. So an easy way to look at a not weird, just coordinate pair graph and decide if something has an inverse is to perform the opposite of what you're used to performing. Oh no, it didn't stick. Let's try again. Okay, the inverse of a relation is a function if and only if the relation passes the horizontal line test. We're so used to doing the vertical line test. The vertical line test is used to determine if a graph is a function, but the horizontal line test is to determine if the inverse is a function. So what we're going to do in these 3 examples is talk about the relation that you see as well as its inverse, which you don't see. It's not graphed. But if we look at this first function, who can name what type of function that is? Cubic. That cubic function, is the cubic function you see a function? I just kind of gave it away. Does it pass the vertical line test? Yeah, so this one would be a function. We'd say yes, it is a function for f of x. But now we can answer the second question, which is the inverse a function? No, because if I drew a horizontal line right here, it would touch the graph like 3 times. This does not pass the horizontal line test, so its inverse is not a function. Yeah, for the second one, is it a function? Yes. Is its inverse a function? Yeah. It passes both the vertical, if I draw all of those, and the horizontal line test. At no point does it cross one of those lines more than once. So we're good. Passes both. What about the third one? Is that showing a function? No, because if I drew a vertical line here or some other places, it would repeat the x's, so it is not a function. But is its inverse a function? Yes. Yeah. So they don't have to always agree like the no's and the yeses. A relation can have an inverse that's a function and vice versa. Okay, so you notice something looks different on these notes. There's a lot of algebra going on in these problems, and I didn't want to spend forever having you guys try to quickly write down what I've been writing. So I've already written in the work for most of these problems, and exactly what I've done, and then you're going to be able to take those skills and apply them to other things. Let's talk about finding inverses algebraically. A function passes both the horizontal and vertical line test is said to be 1-to-1, which is what we're working for. We want functions and we want inverses to be functions. To find the inverse algebraically, this is super important right here. We're going to switch the x's and y's and then resolve the equation for the y. And that's where all the algebra comes in. We're going to switch the x's and y's, all of them, and then resolve the equation for y. Important note here, though, the range of f of x, which means that we need to find the range of f of x every time, will become the domain of f inverse. That's super duper important. It's very tempting to try to go domain to domain. It's not. The range of the starting function will be the domain of the ending function. We very rarely looked at the range of functions, so we'll have to do that today. So if we look at this first example, which I know I wrote all of this in green because I was using a green pen and it just like somehow scanned in green. Yours is in regular black ink, so you can annotate it how you would like. Here's what I did to find the inverse and state its domain. First things first, I thought about the type of function I was using and wrote down its range. What type of function is f of x here? Cubic. The end behavior of cubic is that it goes off to infinity both ways, which means its end behavior is from negative infinity to infinity. If you think about the shape of a cubic, it goes all the way down and all the way up. Okay, cool, got that part. What did I do this next step? It says it, but what did I do? Yeah, okay, so f of x is the same thing as y, so I made that an x, and I made all of the x's a y's. Cool, now I just need to resolve for this y, so I subtract 2 from both sides, and then to get to cube to go away, I cube root everything, and now I have it equal to y. Once y is isolated, that's solving for y, that's the inverse function. So you would just write it as f inverse of x is equal to whatever you got. Cube root of x minus 2.
How would you solve that?
Which what?
How would you solve that? Like, if you did the cube root and stuff.
Well, how do you undo a cube?
Oh, cube root.
Yeah, same way you would undo a square by square rooting, you undo a cube by cube rooting. If it was 4, you take the 4th root. Okay? This is how you would answer the question. This is the inverse function. We just also need to state the domain. But like literally you already figured that out. I don't need to think very hard about it because it is the same as the range that I started with. So we find the range. We hold on to that for later. We switch x and y, we resolve for x, and then we make it look fancy with f inverse of x. Questions before you guys try one on your own? Okay, I want you guys to try B. Just right next to it. You got the steps written right there. I want you to give it a shot. Okay, so here's what we should have gotten. We look for the range, and if you think about a quadratic that has a minus 6 behind it, if I were to graph this, it would just be translated down 6 units before it's a quadratic. So this doesn't go from 0 to infinity on its range. It goes from negative 6 to infinity because we pulled down the quadratic. Okay, we've got the range. We know that's going to be my domain at the very end. So we exchange the x and y, and then we start solving. Plus 6, square root, and we have our inverse. Now here's what's cool. We did find the range originally, and it's important to do that. We also should have probably checked to make sure that there was not an additional restriction from this domain. But check this out. The restriction would be that the stuff underneath the square root has to be greater than or equal to 0, and it ends up being the exact same domain that I started with. That's because they're inverses with each other. So the range of the start becomes the domain of the finish every single time. It's also just the domain of the finish. Questions about this one? Because the next example has some crazy algebra in it. Okay, let's talk about some crazy algebra here. This problem's so much fun. In problem C, f of x is x plus 4 divided by x minus 3. To find the range of a rational function, it's like finding the end behavior. That's Bobo, Botan, and Betsy. This is a Betsy question, which means it would have a horizontal asymptote at y equal to 0, and that it has a break in its its range at 1, the same number. Where'd I get this 1 from, by the way?
Oh, divide the.
Divide the coefficients. The coefficient of the top is 1. Coefficient of the bottom is 1. 1 divided by 1 is 1. That's because it's a Betsy question. Okay? So we're going to switch the x's and the y's. We're going to switch the x's and the y's, which in this case has 2 y's and 1 x, because there was 2 x's over here. No big deal. We need to solve for 1 y. So here's where the algebra gets kind of wild. We are first going to multiply by the denominator on both sides. Basically, take the denominator to the other side. Okay, maybe draw these arrows in with me. Then we're going to distribute this x to the y and the minus 3. I get xy minus 3x equal to y plus 4. I then need to get all of the y's on the same side. So what I did in this next step is I said minus y over here, minus y over here. I also need to get all of the x's on the other side eventually. So I'm going to do plus 3x plus 3x. The positive and negative 3x cancel. The positive and negative y cancel. Do we see how we got from that step to the next one? We moved the y and we moved the 3x. The next step to go to the next line, since both of these terms have a y in them, I'm going to factor out a y. Basically, undo distribution. So basically, take the y to the front as if it had been yanked out of both of these. Backwards distribution. And I'd be left with x minus 1. Since I now only have 1 y remaining, I can just divide away that parentheses x plus 1 so that y is isolated. And that's the inverse. Whoa. What step where? What do we need an explanation for? Okay, so I've divided, or I multiplied by the denominator. Basically, it like kind of comes over to the other side because it crosses out on the right-hand side. We distribute. The next step, when I move the y and the x, I did 2 steps at once. I subtracted the y and I added the 3x just to get them on the correct side. All of the y's on the left. We factor out a y. And once we factor out the y, we can divide by this x minus 1 because the x minus 1 would cancel out. And we'd have y by itself. Oh boy. But then we have our inverse function. F inverse is equal to 3x plus 4 over x minus 1. And we would use the range we found originally as the domain of the new function. But if you checked, and I showed you right here in my little check, that denominator cannot be equal to 1 because this cannot be equal to 1, but that's already taken care of in my domain. So it's like another little check right there. Let me give you some time on this one because part D is kind of exactly like this one. So I want to give you some time to think through it. Find me the inverse and state its domain for part D. Okay, I'm going to start to go through it, but I just paused here because I feel like maybe hearing it and watching it live would be helpful. So we found the range. This is again a Betsy question because the bottom exponent equals the top. So you divide the coefficients. 2 divided by 1 is 2. So this domain is everything but the number 2. We would multiply the denominator to both sides, which would cancel it out on the right side, but not cancel it out on the left side. So it would be y plus 2 times x, or x times y plus 2, same thing. We would distribute this x, bless you, this is xy plus 2x, I don't know why I put that parentheses there, I'm going to get rid of it, equal to 2y minus 1. I'll go one step at a time here. I'm going to subtract 2y from both sides, bless you, so that I have xy minus 2y plus 2x equal to negative 1. I'm going to subtract 2x from both sides. So we subtracted 2x from both sides. That'll cancel the 2x's out. This is xy minus 2y equal to negative 2x minus 1. So those are two steps I did not show in what's written on your paper if you want to have that down. We factor out y, which is like dividing out a y. These y's would disappear. This would be x minus 2 with a y in front. We divide by that parentheses so that y is all the way by itself. Negative 2x minus 1 over x minus 2, which we know if we just write it in the fancy little inversed version would be f inverse of x equal to negative 2x minus 1 over x minus 2, given that its domain was the range that we started with, which is everything but the number 2. Again, that makes sense because the domain of this rational function tells me that.
So the domain is always going to be the same. Right?
As the range of the original, yes. That's how they're related to each other. Okay. Questions again after we saw a second one for this type of problem? Yes.
Go back to the first one. I didn't finish.
Yes. You're welcome. So the reason I highlighted x minus 2 here at the end is because that, if I would just gave you this equation and told you to find the domain, you'd be like, that's a rational function. The denominator cannot be 0, which means x can't be 2 because 2 minus 2 is 0, right? But that makes sense because we already said the domain does not include 2, but we just said that from the range. That was just a quick check to make sure that it still agrees. Huh? We might not have time. Okay, let's go to the next question. Again, I've done one of them for you. This problem is very, very interesting to me because of the type of function we started with. What type of function did we start with? A square root. What's the range of a square root? 0 to infinity, because it goes from 0 off to infinity. That's what this graph would look like if I were to graph it. So cool, we've got the range, because we remembered what type of function we were using. Starts at the origin, this one's been translated to the side, goes up. So we switch the x and y. We would square both sides and then isolate the y. That's all solving for y again. So it makes sense doing the inverse. However, if we were to just graph this, this is a quadratic that looks like this, right? The whole thing is the quadratic, but we have to say that because this is just the inverse of this, its domain is only from 0 to infinity. So for it to graphically make sense as its inverse, we don't include all of this right here. In fact, mark it out. All of that is not a part of my inverse function, because otherwise the shapes are not reflections of each other. Do you see how this shape and this shape are kind of like flip-flops of each other? That should happen. You can't go from this to a whole thing like this. That's not flip-flop shapes. Reflected across y equals x. Okay? Can you guys try example F for me, just right next to it? Something very similar. Oh, it didn't stick. Okay, so here's what we should have gotten for the inverse. It's x squared minus 5. But for its domain, if I were to not think about the range of what I started with, the domain of any quadratic is all real numbers, but we can't answer that for it to be its inverse. We'd have to agree with the range here that the domain is from 0 to infinity. So don't let that trip you up if at the very end you're like, but I have a quadratic, so it's all real numbers. Not if what you started with is something that is not also all real numbers. They have to agree. Yes? Fabulous. Okay, so now that we get what inverses are, we also need to be able to algebraically verify that things are inverses. So this is going to be a little bit of a review of what we did last class, because the definition of two inverses algebraically is as follows. Two functions, f of x and g of x, are inverses if and only if both of the following happen. If you could do f of g of x, and when you do compute all of that, you get x. And if you reverse it, g of f of x, you also get x. So we are going to have to compose them both directions, f of g of x and g of f of x, and hope that both times we get out x, and we have confirmed that they are inverses, that they undo each other. That's undoing the function. Okay, so let's do that. We'll go through f and g. So this is just function composition like we did last class. Here's f. Here's g. We would do f of g of x. So we have 1 over 2. Sorry, I did not show you that the way I wanted to. This would be f of g of x, meaning that I'm plugging 4x plus 8 into the f function. So anywhere in the f function there was an x a second ago, now I'm putting 4x plus 8. I just composed them. Now we're going to simplify it and hope that it comes out to x, because if it does, we're halfway there. Multiply, multiply. 1/4 times 4 is what? 1, so 1x. And then 1/4 times 8, or 8 divided by 4, 2. And then we can simplify. Positive 2 minus 2 are going to cancel each other out. That is equal to x. And we're good so far. We have done f of g of x and got x. We're halfway. Now we verify the opposite direction. We do g of f of x. Can you guys do this one for me?
Yeah.
You got it. I heard yeses and nos. We can do it though, guys. Thank you for your honesty. So once we've done both function compositions, f of g of x and g of f of x, if both of them come out to x's, then we can say that we have verified. Therefore, f of x and g of x are inverses. That's how we verify. So if someone is just like, I'm pretty sure these are inverses, you'd be like, hold on, let me check. Check it like this, and we verify that they are inverses. Now they can be nice and pretty, like this. Linear function and linear function. But there is also inverses of functions, like we found a second ago, where you start with a rational and you end with a rational. So if you flip your paper over, you're going to see an example of that. I've already done one of them for you because it's also some wild algebra. But on the back here, I've set up for you, I've done one, so let's talk through what I did before you try one. Yep, maybe get your highlighters out here. What I did was I took f of g of x, right, f of g of x, which means anywhere inside the f function that I saw an x, I'm going to plug in 3x plus 7. Now, unfortunately, that's 2 places. Because a second ago, don't write this on your paper, this was an x, and this was an x, if you look at the f of x function. So I'm plugging in another fraction inside a fraction to have a lot of fractions happening at the same time. Okay, who can tell me what happened from the first line of this problem to the second? Who can see it?
No.
Just a no. Something similar to what we did, I guess earlier today. Something about the denominator. What did I do with it? So what's happening here? Do you notice that this denominator right here is now multiplied by the 2 parts that were not multiplied by anything? That's what's happening. We are basically giving them like denominators in 2 separate instances so that I can actually add the top together and add the bottom together. Okay, so what I could show you how this works, but it takes like a whole piece of paper to show you literally that step. So what you can think is that this denominator that's in a denominator, you're going to multiply it by the number that's chilling by itself. You see that? It comes out of the denominator, gets multiplied by the part that doesn't have that denominator. Okay, from the second step to the third step. So from here to here, what did I do? I distribute. We know how to do that. So we would distribute the 7 and distribute the -3. Make sure you distribute -3. And then I'm left with that third line. Do you notice some cool things about the third line? Probably this. Watch the board. Watch the board. Oh. Some things cancel out. I'm left with 10 x's on top and 10 on bottom. 10x divided by 10. The 10's cancel out, and I'm left with x. It's some wild looking algebra, but we get x. Your turn. You've got g of f of x. It's going to work very similarly, so look at the example or flag me down and ask a question. Okay, let me go through this one because I'm seeing some really good ideas, and then let's clean it up. So we're doing g of f of x, which means I'm taking the g of x function, and everywhere I see an x, I'm plugging in, I already forgot the equation. What is it? X plus 7, x minus 3. Thank you. Okay, so we do that. This is going to be 3 times x plus 7 over x minus 3. Is it minus 7? Plus 7 again. What? Over x plus 7 divided by x minus 3 minus 1. Right? I heard a bunch of what, so what is the what for? Where did I get the 3 for? Great question. It's in the g of x function. There's a 3 right here. So it's 3x, but the x is this whole thing over here. Well, this is the f function that I'm plugging in. G is the outside one. Okay? So here's where I'm seeing all of the mistakes happening, which I assumed it would be because this step is super weird. You're multiplying by the denominators technically to create a like denominator so you can actually add the numerator and denominator together, which is kind of crazy. So here's what we would do. We would multiply the whole top by that denominator, but it only affects the second part of it. All of us lost this 3. This 3 is still here. So the 3 is still here. Then we do the same thing in the denominator. We get x plus 7 kind of breaking free of its fraction, and we multiply -1 times x minus 3. We distribute. There's 3 distributions to do this time because we had a coefficient there, and we got all these to multiply. This is 3x plus 21 plus 7x minus 21 all over x plus 7 minus x plus 3. I will pause. Okay. Did we all just lose the 3?
Yes.
Okay.
Yes.
I figured that would happen.
Okay.
But now we won't forget about our 3s later.
We will.
Oh, we will. Great. Oh, great.
Wait, so where did the plus 7 and minus 1?
Where did the plus 7 minus 1 come from? Great question. It came from the g of x function again. Plus 7 minus 1.
So you just take the numbers that are at the end and you just...
Multiply them by the denominator. Oh, so, okay. I understand your question. So everybody look for a second. Don't write this on your paper because it will totally mess you up. If you ignore the red, in blue, I have written 3x plus 7, x minus 1. That's the g function, right? But I'm not plugging in x's. I'm plugging in all of this. So everywhere there was an x a second ago, now I put that f of x function in its spot. Even if there's a coefficient in front of it, you just pop it in there.
Oh. No.
No?
Okay, I get it.
Okay.
No. I think I get it.
Okay. When we finish this one, we're at the last little step here. We've got positive and negative 21, which will cancel out. Positive and negative x, which will cancel out. We have 10x on top, 10 on bottom, which gives us x, so it's verified. Therefore, f of x and g of x are inverses. It's probably stopped. Refresh your screen.
Alright, wait the half now.
So we will stop here. We will finish with that example later, which means I'm going to assign your homework and I'm going to leave all of the problems there. But when you get to the part where it asks you to find and verify, if you can't do it because we haven't done an example yet, just hold on to your homework. It won't be late if you need an extra day to finish it.
Yes.
That's a great question. Here's your homework problems.